Alright, welcome back. So today we are going to be looking at energy and enthalpy, so basically describing what enthalpy is and looking at how to calculate it and what it means for thermochemistry in general. So first we're actually going to define what enthalpy is. Now just remember that the kinetic energy from molecules comes from the moving of the electrons, the vibrations of atoms within the bond, and generally how they're moving. Whereas the chemical potential energy is the energy stored within the bonds within a substance, and even the intermolecular forces between substances, because that is still a chemical bond. Now, enthalpy is the total internal energy of a system. So if we're able to calculate the sum of all the kinetic and the potential, we would then classify that as enthalpy. Now, sadly, it is impossible to measure enthalpy of individual substances because we can't really calculate the kinetic energy of molecules. You can with a thermometer, I'm sure, but that's just kind of the average and all that. But the thing is, how do we actually stick a probe and measure the energy inside chemical bonds? Which we can't. There's just no way for it. So we need to find a different way to calculate that. And that is where we're going to look at enthalpy change, which we're going to refer to as delta H. So this refers to the changes in potential energy, because all a chemical reaction is that we're changing potential energy. We're breaking bonds and forming new bonds. So that is how we're going to get around this. We're going to look at the change when we do a reaction. Because observation is what we know right now, because when we change to potential energy or change the potential energy between reactants and products, it's going to equal to the amount of heat absorbed or released by our reaction, which is basically the first and second law of thermodynamics put into one, because we know energy needs to be transformed into something. It can't be created nor destroyed. That's why the energy universe is constant. And of course, energy runs from hot objects to cold. So heat is released or absorbed to the surroundings in a chemical, physical, or nuclear change. We're only going to be worrying about physical and chemical. We're not going to do nuclear. And energy lost by the chemical system is always equal to the energy gained by the surroundings. So basically, Q out is equal to negative Q in, because they're going to be the same number except opposite. So what we normally do is we normally use kilojoules for these here, but we're going to pay attention to, questions and all that and what is there. Now, sometimes you will notice subscripts. Don't be scared of them. They're just going to give you an idea of what reaction's going on. So sometimes if you see delta, so the change in enthalpy with R, what that means is just change in enthalpy of a reaction. That R stands for reaction. And some of the common subscripts we'll see are C, F, and D, which stands for R, any reaction, C, complete combustion, F, formation, or D, decomposition. So that just tells you what the reaction is. So you may see them, you may not. You may use them yourself, you may not. Doesn't really matter. They're just there to give you more information. Now, sometimes you might see a little circle above there as well. So this means that it takes place at standard conditions. So you might see delta R H naught. And this just means the standard enthalpy change of a reaction, right? And standard just means that STP, 100 kPa, and 25 degrees Celsius. Now, the other thing we're going to get is something called molar enthalpy, which is designated H. So notice that it's not change in enthalpy, it's not delta H, it's just H. But this is still a change in enthalpy per mole of a specific substance. So our units, for the most part, is kilojoules per mole. Now, what we have right here, I know there's a lot of words right here. We can find standard molar enthalpies of formation, only for formation reactions, on page 4 and 5 of our data booklets. And once again, formation or decomposition. We'll get to why decomposition later, but decomposition is just the opposite of formation. Now, it says right here as well, pay attention, distinguish the difference between molar enthalpy and change in enthalpy. So look for the units given, because units will always tell you. If you see units of kilojoules per mole, this is always going to be for molar enthalpy. If you see units of kilojoules, this is always for the change in enthalpy. This will always hold true. So sometimes, like, a question might forget to put in the word molar, but if you see the units of kilojoules per mole, it's referring to molar enthalpy. All right? Now, how does this relate to reactions? So, we're going to be looking at chemical potential energy. Now, as we already stated, this is the energy stored within the bonds of chemical substances. And thermal energy is going to be released or absorbed when a chemical reaction occurs. All chemical reactions. Sometimes it's hard to detect if it's happening or not, but it does happen. So in a chemical reaction, one substance is converted into another substance, And in a chemical reaction, the process of breaking bonds and bonds reforming occur at the same time. Now, this will always be the case. So when we break bonds, this requires energy, or it is always an endothermic process. And when we form new bond, it always releases energy, which is always exothermic. So the net energy of a whole reaction just depends on which one is bigger. All right? So for example, this is every chemical reaction. Breaking bonds needs energy. Then the arrow for some reason didn't make it in this here. New bonds forming, and it releases energy. So if energy 1, so this one, if the energy absorbed is greater than the energy released, the overall reaction is going to be endothermic. An example that we are going to have, photosynthesis. Now you will need to memorize this equation and where the energy unit goes and the states of matter. So, photosynthesis, what do we have? It starts off with 6H2O, and it needs to be a liquid. Because remember, if you have plants, you water your plants, you don't gas them, so it's not going to be H2O gas, and it's not solid, you don't shoot ice at them, right? You pour liquid water onto H2O liquid plus 6CO2, and CO2 is a gas, plus energy. In this case, normally in the form of light. It produces glucose, C6H12O6, and plus 6O2 gas. And please, please, please pay attention to the liquid water there. That is very important. Now, what we're going to see as well is that endothermic changes are always going to be designated as positive values since energy is being added to the system. So it's almost like a reactant. Now, if we go back, remember energy 1, or apparently how I spelled there, energy, should be energy. So if energy 1, so that is if the energy absorbed is less than the energy released, the overall reaction is now exothermic. And the common exothermic reaction you're going to have to know is cellular respiration. So this one is the exact opposite, like everything is the exact opposite of photosynthesis, where we start with our glucose, so C6H12O6. Now, I forgot the state of matter up here, didn't I, for glucose? And that's going to be aqueous. Sorry, that's an AQ. And I'm going to remember to put it down here as well, AQ. So we have aqueous glucose plus oxygen gas. It's going to produce, in this case right here, 6 carbon dioxide plus 6 H2O liquid, and plus energy in the form of ATP for those of you who done bio. Now, once again, liquid water and carbon dioxide are gas being produced in cellular respiration. So it is just reverse of what glucose is. Now, you will notice the fact that we have something like this, so glucose looks like a hydrocarbon because it contains carbon and hydrogen. It's reacting with oxygen, producing CO2 and H2O. So you will notice this is very similar to hydrocarbon combustion. Now, hydrocarbon combustion we've done before, right? But we are going to learn 2 new things, and this comes down as our note right here. Hydrocarbon combustion can happen in an open system or a closed system. And depending on what we're dealing with, you have to know the products. Now, we can read right here the note, gaseous water, so H2O gas and carbon dioxide gas are products of hydrocarbon combustion in an open system. But in a closed system, we get carbon dioxide and liquid water. So you do have to be careful about how you're representing combustion reactions in this unit as well. So for an open system, I'm just going to take the combustion of methane. So CH4 gas plus. Now we know all combustion reactions need to react with oxygen gas. And in an open system, it's going to produce CO2 gas and H2O also a gas in an open system. And then, of course, balance and combustion reactions, we know it produces energy. So all combustion reactions in an open system is going to have the water as a gas. Now, if it's a closed system, now if we do the exact same reaction, but we do it in a closed system, now we're going to get water coming out as a liquid. So that is one major distinction that you're going to have to remember. And it will come down to some of the questions as well. It might just say something is going to happen in a closed system, and you'll need to know that it's liquid water. Especially when we get going, just to kind of give you an idea as well, it's going to get brought up later. The reason why we need to take note of that is that when you look at your data booklet here, water, if you're forming liquid water or water vapor, they have two different enthalpies of formation. So that means that we can tell right here it takes more energy to form liquid water than it does water vapor. So that's going to affect our calculations if you put in the wrong one. Now, when we're dealing with exothermic reactions, we are going to designate them as negative values, since energy is being released by the system. So it's going to be a product in the reaction. Now, this is just an old diploma example, and I believe, so if you just look at that, so just pause the video right here, and in 3 seconds, the answers will go. So pause it and just see if you can get it on your own, and I'm going to put the answers up in 3 seconds. All right, boom. So of course our answers, reactants and photosynthesis. We have CO2 gas and H2O liquid, and products, hydrocarbon combustion in an open system. It's CO2 and gaseous water. And if you look on the next page, we do have another diploma example. So same thing. I'm going to put the answer up in 3 seconds, so just give this a try and see if you get the correct answer. And boom, your answer should be B. So just now, right before we go to our last one, just on the last page here, this is just a little chart summarizing endothermic and exothermic reactions. All right, so for endothermic, we know system absorbs energy. Temperature of the surrounding is going to decrease. That's why endothermic reactions always feel cold, and our enthalpy value is going to be positive, and the energy is shown as a reactant. So our example is photosynthesis. Now, just remember, like, kind of an idea of what's going on. Now, this is going to be a very, 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 very crude diagram of system and surroundings. So in endothermic reactions, energy here is going to be in red. What is happening is that energy is going to leave the surroundings and go into the system. So that's how the system absorbs energy. It's taking it from the surroundings. And here the red arrows are energy. All right, so that is why, like, if there's an endothermic reaction and you touch it and it feels cold, it's because energy is leaving your hands and going into the reaction. All right, now that's opposite from our exothermic reactions, where the system, our reaction, releases energy into the surroundings. So the temperature of the surroundings increases, and the enthalpy value is going to be negative. And if we write out, the energy shown on the product side. Now, our example that you need to have remember is cellular respiration and, of course, combustion reactions. But if we did out, same thing, a very crude diagram of general exothermic reactions. We have our surroundings, we have our system, and if we looked at the energy would leave our system and go into the surroundings. So this is why for exothermic reactions, if you are part of the surroundings, you will feel warmth coming from the reaction because the energy is leaving the chemical reaction and going out into the surroundings. So this diagram is going to make another appearance when we get into something called calorimetry, which will be another lesson away. But our next one, ends our second lesson here on enthalpy. So same thing, you can go to the section inside of your workbook and work on those. And come back for next one. We are going to look at our next unit, which you can just see right, oh, sorry, not next unit, our next topic lesson, calculating enthalpy changes. All right, so that is it for this one. So hopefully see you guys later.